Chapter 16, Molar Solubility from KSP. Calculate the molar solubility of lead chloride given a KSP of 8 times 10 to the negative 5. So remember, KSP stands for solubility product constant, and we can use it to figure out the concentration of everything at equilibrium when the solution is saturated. So step 1, identify the major species. Here we are working with lead chloride, which is a salt. We will write out our equation. And let's see, so we'll have lead and lead chloride. I'm going to use a double-sided arrow. We are dealing with an equilibrium constant, a KSP, which means that it will go both ways. And we'll end up with lead and 2 chloride ions. So now we're going to write out our equilibrium expression. Do we need to do a dilution on this problem? Nope, nothing's getting mixed together. It doesn't get diluted. So we'll have a KSP equal to, now remember we are starting with a solid and then it is dissolved, so it ends up being aqueous. So we're only going to include our aqueous substances. We don't include solids or liquids. So there's that. And I'm given what it's equal to, which is always nice. 8 times 10 to the negative 5. And remember, the only equilibrium constant value you should have to memorize would be the water one, Kw, which is 1.0 times 10 to the negative 14th. And actually, you don't even have to memorize that because I believe it's given on your equation sheet. Alright, so now that we have our equilibrium constant and we're trying to figure out concentrations, I better set up an ice chart. I'll write the whole thing on here and label it as a solid. Remember though, we don't include solids, so whoop, that's gone. And I know that I started off with that solid and I did not have any of the ions yet, so these guys are at 0, which tells me, okay, that gets added. When you pick an x, pick something that does not have a coefficient. That way the things that do have coefficients, you just put that coefficient in front of the x. You could do it the other way around, like if I labeled the chloride as x, then I'd have to remember to make my lead be 1/2 x. That's the only trick there. Okay, so now that I've done this, I'm going to solve for concentrations by plugging into my equilibrium expression. Remember, the goal here is to figure out the molar solubility, and in order to figure that out, we need to know the molarity of what we're working with at equilibrium. Oh, equilibrium expression, there's only one. So, I know that my KSP is going to be equal to x times 2x squared, and all of that can be set equal to our given KSP. This should give you an x value of 0.031 sig fig molarity, and I know that is equal to the concentration of my lead ion. So if we want to know the molar solubility, we first figure out, okay, how much of my ions do I have at equilibrium. That'll tell me how much was able to dissolve. So I know 0.03 molarity of lead was able to dissolve. And I know that I have a one-to-one between lead and lead chloride, so that means that the molar solubility of my lead chloride must be 0.03 molarity. In other words, that's a saturated solution there, 0.03 moles per liter. However, usually we report solubility in grams per liter, so let's go ahead and convert that as well. So 0.03 moles of lead chloride per 1 liter of solution. I know in every 1 mole there's 278.1 grams. And that, if I cancel out my units, will give me about 1 sig fig gram per liter of lead chloride in a saturated solution. And that's my answer. So just to make sure we're clear on what just happened, when you want to figure out solubility, you first need to figure out the concentration of your ions, and then for a salt, and then you're going to use that to figure out, well, how much of my original solid dissolved. I know that I have a one-to-one between lead and lead chloride, so that gave me the amount of lead chloride that was able to dissolve, and then I could convert that into grams per liters, which is how we usually look at solubility. So there you go.